Welcome back. In this session, I'm going to continue with the hypothesis testing and introduce the concept of specificity and sensitivity of a binary test. So in our previous lectures, we've talked about the errors that can happen in hypothesis testing, namely type 1 and type 2 errors. Building forth on that, I'm going to introduce the concept of sensitivity and specificity of tests. So for example, let's build a contingency matrix around a test that can happen. So if we have a test which gives a simple yes or no result, for example, it could be a disease test, or it could be a drug test, it could be a pregnancy test, it could be any test which gives a binary result, either yes, no, positive or negative, 1 or 0. So when we talk about a binary test, there are four possible outcomes that can happen. One is the test outcome. So test outcome can only be positive or negative. So as in this case, a test can come out as negative or positive. So either the person does not have the disease, or is drug free, or is not pregnant, or the opposite, that the test senses a positive. So this is the test outcome. And the other is whether the person is actually of the condition or not. So for the person may actually be drug free or disease free, or not pregnant, or is the person actually pregnant. So in this case we have a positive or negative, which is the actual state. I'll just make that better. So let's call this the actual state. So when we have such a contingency matrix, so we can divide this into four quadrants depending on whichever one we lie in. So these are my four quadrants: 1, 2, 3, 4. Now this can be inverted. Positive can be here, negative can be here, and similarly positive on the left hand side and negative on the right hand side. But let's go with this particular instance. So what is quadrant 1? So quadrant 1 is when the test says negative and the person is also negative. So let's take the example of a disease over here. The test came out, let's say it could be Ebola, it could be AIDS, it could be swine flu. The test comes out as negative for the disease, and person is also negative. Actually the person is not sick. So in this case, this is known as a true negative, or a TN. I'm going to call this as a true negative. Let's look at quadrant number 2. In this case, the person is actually positive. The person has the disease, but the test came out as negative, and that's a very big error. So this is a false negative. Let's look at quadrant 3. Quadrant 3 is when the person has the disease, which is the actual state is positive, and the test also sends out a positive result. So this is known as a true positive. Now that means we've captured the condition correctly. And let's look at quadrant 4. Quadrant 4, the test result came out to be positive, but the person is actually negative, i.e. the person does not have a disease. So what do we call this? Positive, but actually not so. So this is a false positive. So these are the four conditions, or these are the four results that can happen when we do a binary test for any particular condition. So we can have true negative, true positive, which is quadrant 1 and 3 in this case, a false negative, which is quadrant 2, and a false positive, which is quadrant 4. So what is the accuracy of the test? How do we define accuracy? So the accuracy is simply the correct conditions divided by the total condition. So what is the probability of being in the correct condition? So if the condition is quadrant 1 and quadrant 3 are correctly diagnosed, divided by the total possible diagnosis. So 1 plus 2 plus 3 plus 4. So all conditions which fall under this is how we calculate the accuracy of a test. So the probability of coming in quadrant 1 or quadrant 3 divided by the total probability across all the four quadrants, that gives us the accuracy of the test. But what do we mean by sensitivity of the test, and which ones are the errors? So we know quadrant 2 and quadrant 4 are the errors. Now if we go back to our presentation here and we test out the condition for a type 1 error. The type 1 error says rejecting the null when the null is true. The null hypothesis always is the person is negative. So when we say the person is negative, right, and we reject it when the null is true. So the actual is negative, but we are testing it as positive, which is quadrant 4. Quadrant 4 is a false positive. So that is a type 1 error, aka also false positive. So the quadrant 4 is also the type 1 error. And what is quadrant 2 then? Quadrant 2 is accepting the null when the null is false, i.e. accepting the person is negative. In this case, we are accepting the person is negative because this is the test result when the person is actually positive. So that's a type 2 error. And as we've already covered in our previous lectures, some kinds of errors are more problematic than the others. In case of a disease test, telling a person that they are positive when they are actually negative has a cost to it. Yes, no doubt, right? We told a healthy person, hey, you got Ebola, you probably die. Here, take some medicine, right? And that's a serious error. But telling a person, hey, you don't have Ebola when you actually have Ebola is an even graver mistake. Not only would the treatment be delayed, but if it's an infectious disease, the person could take some other people along with them, right? So in the disease testing case, we want to minimize type 2 error, and we want to at the cost of type 1 error. Obviously the optimum cases, both errors are minimized, but as we know, by changing the value of alpha of the test, we can control the occurrence of one error at the cost of the other. So in a disease testing scenario, we want to minimize the type 2 error, and we are okay with even slightly higher type 1 error. So this is what a 2 by 2 contingency matrix or the quadrant look like. So we've covered what is meant by true negative, false negative, true positive, and false positive in terms of a contingency matrix. So what do we understand by sensitivity? So sensitivity is the percentage rate of actual positives testing as positive. So what are the actual positives here? So these are the actual positives. And how many are testing positive? Only this. So the sensitivity rate. So I'm just going to, delete a little bit over here and, create some room over here to write it down. I don't want to start with a new sheet. Okay, so we're back, right? So we've covered over here sensitivity is percentage of actual positives testing as positives. So what are the actual positives? Actual positives are quadrant 2 and quadrant 3. So this is this column over here, which is the actual positives. So total number of positives is quadrant 2 plus quadrant 3. And how many are actually testing as positives? So that is this row over here, right? But over here only the quadrant 3 is overlapping between them. So percentage of actual positives actually testing as positive is only 3. So this percentage gives us the sensitivity of a test. What do we mean by specificity of a test? Specificity of a test tells us percentage of actual negatives testing as negatives. So what are the actual negatives? The actual negatives are in this case. And how many of them are really testing also negative, which is this row intersection over here. So this is only quadrant 1. So specificity is 4 plus 1 on the denominator and only quadrant 1 on the numerator. So this is the sensitivity of a test. Sorry, the specificity of a test. So again, a quick recap. By sensitivity, we mean percentage of actual positives testing as positives. So true positive divided by true positive plus false negative. Specificity, percentage of actual negatives testing as negatives, i.e. true negatives divided by true negative plus false positive. And we've already covered a 2 by 2 contingency matrix where the test result is either negative or positive, and the gold standard, the person is actually negative or positive for that particular condition as well. So this can be applied to any particular hypothesis testing where we are having two specific hypotheses or a binary outcome, a yes, no, 1, 0, positive or negative. Examples are disease, drug, pregnancy tests, in any particular scenario. Right now, what I'm going to do is I'm going to use this now and move on to the next exercise where we're going to apply this concept of sensitivity, specificity, and take a real life example. Right. So let's take this example. a company wants to conduct a random test on all its employees. Those testing positive will face administrative action. So this is a classic binary test. Whenever we do a drug test for that employee, the test will come out only as positive or negative, i.e. the person is clean, no cocaine for him, or this person is doing some kind of weed, this person is taking illegal drugs. We need to do some we need to fire this employee or give a warning letter or something. So this is a classic contingency matrix situation where we have a binary result of the test, right? And now the power of the test or the accuracy of the test is defined as test being 99% sensitive and 99% specific. And it is estimated that about 1.5% of the employees will test positive, which is the estimated population mean in terms of percentage of employees on illegal drugs. Right? The question that comes out is this test accurate? Can the result be used for initiating administrative action against employees testing positive? I.e., it doesn't matter, whether we are able to catch all of them or not, but whoever we do catch, can we go ahead and, take some administrative action against those tests? Remember, the test is 99% sensitive and 99% specific. On the looks of it, the test seems very powerful. You're the HR. You test all the employees, a few percent, a very small number come up positive. What do? Do you fire them? Or do you say this test is, rubbish, let's throw it out and let's think of something else? Right? So we have to think about this. Is this test powerful enough to actually go ahead and, take some action? Let's flip it around, Supposing you're an employee who has tested positive. It doesn't matter whether you're on drugs or not. The test is 99% sensitive, 99% specific. This cannot be argued against. This is set in stone. The test results or the power of the test or the accuracy of the test is defined. It is applicable. It is non-negotiable, right? But if you have been tested positive, how will you go ahead and convince the company, right, that this test is not correct, right? That you cannot be held responsible or you cannot be fired because of the result of this test, right? Now we're going to take this and take this case study and prove how sensitivity and specificity are not enough to action. Let's take this example. So I'm going to start off with a clean contingency matrix. Let's start this off with the actual drug usage of the company, sorry, of the organization. In the actual usage, the person can either be negative or the person can be positive, i.e. the person is either taking drugs or they're not taking drugs. And then let's talk about this as the actual result of the test as well. The test can only come in two shapes. Either the test turns a negative or the test turns a positive. So let's call this as the test result, right? And this is our contingency matrix in this case. Let me draw this out, and just to make it look better, I'm going to give this all a white background. So this is the positive, negative, actual as well as tested. Now we know that the sensitivity is 99%. We also know the specificity of the test is 99%. We know that the estimated positives in the company is about 1.5%. So this is given. This is set in stone. These are the assumptions that we are going to work with. Right? So what percentage or what is the likelihood that this test will commit an error when they are detecting drug positive people? So again, we've set up this situation. The company is going to do a random drug test on all its employees. The test is 99% sensitive, 99% specific. About 1.5% of the employees are supposed to be positive on drugs, and the company wants to detect them and they want to initiate administrative action against those people, right? And the setting of the test is that you as an employee have tested positive. How would you build a case so that you don't end up losing your job, right? So we've created this scenario. Now what does sensitivity mean? Let's go back. Sensitivity means percentage of actual positives testing as positives. So we know the actual sum of positives. So assuming there are the total number of employees are, let's take a round figure, there are 1,000 employees, right? So what percentage of employees are on drugs? We know that the estimated positive is 1.5%. So the actual number comes out to be, so I'll just multiply 1.5% with 1,000. So we know total 15 people are on drugs. So the summation of this column, which is the percentage which are actual, will be 15. Right? So how many are not on drugs, which will be the summation of this column? So the summation should be total employees minus those who are on drugs. So we know that 985 employees are not on drugs, 15 employees are on drugs. Now we're going to figure out how many total test negative, how many total test positive. And we're going to apply sensitivity and specificity over here. Sensitivity, percentage of actual positives testing as positive, right? So actual positives testing as positives is this number or this quadrant over here, right? And this is supposed to be 99%. So I know that 99% of the people who are actually positive, which is 15, will test positive. So approximately 14.85, everybody, almost everybody. And how many of those who are positive will test as negative? Simply the column total minus whichever is going into this quadrant over here. So this sum total comes out to be 15. So we're going to ignore these integers that are coming. So we typically don't have 14.85 people, testing positive and 0.15 people testing as negative. So because we've taken the number as 1,000 employees, it could be 10,000, it could be 100,000, it could be only 100. So we're going to let this number be as it is because they represent, we can represent them as raw percentages as well, right? Now, what is specificity? Specificity is percentage of actual negatives testing as negatives, and we know specificity is also 99%. So we know that this is the negative testing as negative, and this is supposed to be 99% of 985. So how many are going to fall into this quadrant? This is the total number of negatives, 985, and 99% of them will test as negative. So approximately 975.15 will test as negative. So how many will test as positive? It will simply be the column total minus the first quadrant. So 9.85 will test as positive when they're actually negative. So what are the total number of people who will test negative? Total number of people testing negative is 975.3. Total number of people testing positive on this test is 24.7. So here we've conducted a drug test on 1,000 employees where the test is 99% sensitive, 99% specific, estimated 1.5% of the employees are on drugs, right? So out of this, we've got the summation, or we've got the result. 975 employees tested positive for drugs, and almost 25 employees tested, 975 tested negative for drugs, and almost 25 tested positive for drugs. And you are one of those 25. But therein lies the rub. Out of those 24 people who have tested positive for drugs, only 14 are actually on drugs. The rest 9.5 are not on drugs. So there is an error in the test. So if you have tested positive, the probability that you're actually positive is 14.85 divided by 24.7, right? So there's a 60% chance that everybody who's tested positive is on drugs. Therefore, 1 minus 60%. So there is a 40% chance, right, that the persons who have tested positive are actually not positive, and this is what you will bring to the notice of the HR, right? While the drug test is 99% sensitive and 99% specific, right? And most of the people who have tested negative are overwhelmingly negative. So the percentage of people who are negative, the percentage of people who have tested negative actually being negative is in excess of 99.9%. But if we look at those who have tested positive, almost 40% of them are likely to be false positives, i.e. they are actually not on drugs but testing positive on drugs. And with an error so large, no administrative action is possible because there's a very large percentage who are actually not on drugs but testing positive on drugs. As you can see, even with 99% sensitivity and 99% specificity, one kind of error can actually be very large. But on the other hand, out of those who have tested negative, 975, how many are actually positive? It's very simple, 0.15. These are people who are actually positive but testing negative, divided by the total testing negative. And we turn this into a percentage. So 0.02%, right? So what this test does is it is catching almost everybody who is on drugs. Literally nobody who is on drugs has escaped this test. But because of the way this test is designed, it has also caught a lot of people, this green quadrant over here, who are not on drugs, right? So almost everybody, 14.85 out of 15 who were drugs on drugs have been caught out by the test. But this test has thrown a wider net, and it has also netted people who are not on drugs. So these 24 people contain almost everybody who is on drugs and and a set of people who are not on drugs. But these 975 people are effectively clean. So if I were the HR, I would not fire these 24 people again, right? But maybe subject them to further tests going forward, right? So based on one test alone, we can't fire anybody because 40% of those 24 people testing positive are actually, false positives. They are not on drugs, right? But everybody who is on drugs is within the sample which we have extracted over here. So these 24 people represent everybody in the company who is on drugs. But unfortunately, they also contain a lot of people who are not on drugs. So this test cannot be used in a legal way, but it can still be used to have, identify a pool on which the HR might want to keep a close eye on. And this is an example of how sensitivity and specificity, even though they may be very high, can actually lead to misleading results on one side or the other. And we need to be very sure that whenever we say the test is 99% sensitive or 99% specific, can it be used? Well, it all depends, So there's no set answer, there's no set technique, or there's no set key sensitivity or specificity result that we are always gunning for. And shortcuts to this is, let's say if you want a test which is 100% sensitive, what do we do? Right? So sensitivity is percentage of actual positives testing as positives. What if I test everybody, all 1000 employees test positive on drugs? What will happen? Everybody who's on drugs is testing as positive, right? So we achieve 100% sensitivity at the cost of 0% specificity. On the other hand, what is specificity? Percentage of actual negatives testing as negatives. So if I test all 1000 employees as negative, I give a blanket negative result to everybody. Obviously, all those who are negatives are actually ending up as negative. So my specificity jumps up to 100%, but my sensitivity goes to 0, right? So having 100% sensitivity at the cost of 0% specificity is simple. Having 100% specificity at the cost of 0% sensitivity is simple. All you have to do is you have to test everybody as positive or everybody as negative. Having both very high requires actually a very accurate test. And even in cases we are able to push sensitivity and specificity up to 99%, it may not be enough. As we've seen over here, out of those testing positive, almost 40% of them are actually not positive, right? But out of those who are testing negative, right, almost 99.9% of them are negative, right? So one kind of the error is very small, the other kind of error is very large, even still over here, right? And this was an illustration of sensitivity and specificity of binary tests. In our next class, we will be moving on with the two sample hypothesis testing. So till now we've covered hypothesis testing or Z oblique T test using one sample. In our next sessions, we're going to be going ahead with two sample testing. So I'll see you in the next lecture.